Don't clap yet, this could be terrible. The musicians wrote their music in 2 days. I wrote this talk in 20 minutes. That's the academic way, do it at the last minute. As Kaylee mentioned, I do a bit of science television. If I look familiar, it might be from the nature of things. They let me host it once or twice this season. I guess it's when they put David Suzuki back in his cryopreservation chamber. Whatever they do to keep him going, he's 80, he should have retired, it should be my show by now. He just keeps going. I did Daily Planet for a long time too. I was there for many years as Zaya Tong's fill-in when she was on assignment or on vacation. You might also just recognize me from the bar around. If I'm not doing science, I'm usually drinking fermentation science. So hello to everyone. It's a pleasure to combine talking about science, drinking about science, and joining you all on stage at the Fox, which my parents are probably really mortified about. Like, Gardy, this is why you were supposed to stay in school, so you're not on stage at the porn theater. But as Kaylee mentioned, in addition to talking about science on television and drinking and talking about science, one of the things I do is actual science. I have a real scientific job, senior scientist at BC-CDC, assistant professor at School of Population and Public Health, where Kaylee lives at UBC, woo, for SPPH. But yeah, I work here at BC-CDC. This is it, so lovingly rendered in watercolor, relaxing, soothing. How many of you actually knew we had a CDC? Yeah, some woots. That's excellent. Infectious disease never gets woots. Curing childhood cancer, that always gets woots. Make the kids healthy again. But infectious disease, nobody's ever like, herpes, woo, yeah. They should be. It's interesting. So, for those of you who didn't know, those of you who neither put their hand up nor wooted, this is CDC. We have an entire building full of people whose job is to keep you safe from whatever's out there. This week it's beaver fever, believe it or not. I got the email in my box this morning, last week, and I realized I just said the words beaver and box in really close proximity to each other on the stage of the Fox. So I'm just killing it in the STI potential division here. So we do a lot of stuff, last week was accidental mushroom poisoning. It's basically kind of whatever is making you weak this week. But this is us at CDC. And at CDC, as Kaylee mentioned, I do this. I do something that is called genomic epidemiology. And genomic epidemiology is essentially reading the whole genome sequences of pathogens taken from an outbreak situation to figure out what happened in that outbreak. So if you've got a bunch of cases of tuberculosis, you've got a bunch of cases of measles virus, we'll sequence all those mycobacterium tuberculosis genomes, we'll sequence all those measles virus genomes, and we'll look for clues. We'll look for little signals in those genomes that will tell us exactly who infected who in that outbreak. And this was a technique that wasn't possible until about 5 years ago when DNA sequencing technology really kind of changed for the better. Our group was the one that really kind of pioneered it. I peaked early in my scientific career with a New England Journal article in 2011 introducing this technique to the world. It's something that public health agencies all over the world, CDC in Atlanta, Public Health England, Public Health Agency of Canada, they've all kind of picked this up and they're all doing it to investigate outbreaks. It's basically changed the way we do infectious disease control. It's totally revolutionary. I get to talk to Bill Gates about it in a couple of weeks, which is super exciting. And I'm not actually here to talk about it this evening. I talk about this all the time. This is my bread and butter. This is what I do every day. It's actually really not that interesting. What is interesting to me as a public health professional, as somebody who stays up at night, worrying about infectious diseases, the thing that really keeps me up at night and wondering, the thing that I want to talk to you today about, something that's really serious, is this. What are we gonna do when the zombie apocalypse happens? I know there are people in the audience who have thought this through. This is nerd night. Like, this is the perfect demographic for this. How many of you, at some point in your life, have given some thought to what your zombie apocalypse preparedness plan is? Exactly. Way more people than have heard of CDC. Okay, I'm not offended by it. By the way, we are located at 655 West 12th Avenue. In the event of a zombie apocalypse, you may wish to knock on our back door. Zombies are awesome. I love zombies. Anybody that's interested in any sort of doomsday scenario, anything infectious disease, thinks zombies are fascinating. And I also like zombies because of their science communication potential. It is Science Literacy Week this week. I do loads of science communication stuff. And zombies are an extremely effective science communication tool. CDC in Atlanta, the CDC mothership, they famously got people to give a shit about public health emergency preparedness, which is like the least interesting part of public health. Public health is full of good stuff. There's Ebola, there's flesh-eating disease, there's accidental mushroom poisonings in BC, but nobody cares about emergency preparedness. Nobody's like, oh, I better check my water stocks and make sure I have enough canned food to survive the apocalypse. But CDC actually got people thinking about this when a few years ago they did a zombie campaign. They said, okay, what if there were a zombie apocalypse? What would you do? Are you prepared? And people really got into it to the point where when it still existed, you could go to CDC's gift shop. It no longer exists, to my great disappointment, and you could buy a CDC zombie preparedness t-shirt with the little logo. All you can buy now is coffee mugs and onesies for babies, which is kind of weird. I did actually get one for my neighbor's baby. She works in public health too, so I was like, look, this is a perfect accoutrement for your future disease controller. You probably actually, if you get a CDC onesie, you're probably obliged to send any sort of fecal material that ends up in the onesie to CDC for analysis. It's basically some sort of clever tool that they're using for molecular surveillance. I don't know. But zombies, effective science communication tool. You take any concept in public health, if you explain it in terms of, something boring like amoebic dysentery, nobody's going to listen. You explain it in terms of, walking hordes of the undead, and suddenly people pay attention. So what I thought I would do tonight is just walk you quickly through 3 vignettes of things that we do in public health that we would do in a zombie apocalypse. So, what the fuck are we going to do? First thing is answer the question, what the fuck is this thing? If you've got a zombie outbreak on your hands, obviously the first question you want to answer is, what is the agent that is responsible for this? This is going to help you design, therapeutics, vaccines, a cure, you name it. So, if you look in nature, you'll find actually a fair number of examples of zombieism. You'll find parasites, all sorts of fungi that will take over their host and zombify it. If you are a frequent nerd nighter, Kaylee has spoken about this before, it's always parasites and fungi that do this. But if you look at the zombie canon, in terms of movies, in terms of television, novels and things, it's not parasites, it's not fungi, it's always a virus that's causing the zombie outbreak. And this makes sense because viruses move quickly. You watch a show like The Walking Dead, somebody gets bit, in a couple hours they've got a fever, a few hours after that they've turned. Viruses work on that sort of speedy scale. So the first thing we would have to answer is, what virus is causing this outbreak? And that question of what novel virus has suddenly appeared in our population is something that we as public health deal with on a fairly regular basis. It's not an everyday basis, fortunately, but it's a regular basis. Every couple of years we encounter a new threat. SARS, many of you were probably around for SARS in 2003 in British Columbia. It was an infectious disease that emerged out of Asia and reached our shores and hit Toronto really hard. Middle East respiratory syndrome, MERS, also caused by a coronavirus. Zika is not really an emerging disease. It's been around since 1947, but we're just kind of understanding it for the first time. Nipah virus about 15 years ago. Nipah virus is actually the inspiration for one of my my favorite scary disease movies. I actually got into infectious diseases. It's really embarrassing. I saw Outbreak, which is a horrible film. It's a horrible film. Do not pick your career based on a Dustin Hoffman movie like I did. It turned out okay for me, but Contagion did a much better job. They had a very good consulting virologist, and they used this story, the emergence of the Nipah virus, which came out in Malaysia about 15 years ago, as the inspiration for the virus. I love this movie because Gwyneth Paltrow dies. It should be pointed out, not unlike her movie career, it is not, she doesn't die until she sort of unleashed this horrible pox upon the world. The same could be said for her lifestyle. Yeah, her weird, her colon spa. Did anybody see the colon spa or the vagina spa? You can steam yourself to better health. Don't listen to Gwyneth. She's a terrible person. You get to the end of the movie, if you didn't, just sort of rewind Gwyneth's death scene over and over again, and you actually made it to the end of the film, you would have seen how a virus jumped from a bat to a pig to humans, and via Gwyneth Paltrow to the entire universe. And that's really the story of how a Nipah virus spilled over. So when we see a novel virus like Nipah, like SARS, what do we do? How do we figure out what it is? In the past, it used to be kind of a two-step process. And the first step was to isolate the virus. We would have to get tissue from somebody that was sick, and we would physically actually have to look for the virus. Typically using microscopy, we would find it, we would isolate it, we would grow it up in a dish, we would culture it. And then, after we'd cultured it, we'd break it apart, pull out all the DNA, sequence the genome, and figure out what makes this thing tick. These days, we can skip over that first step, and we can basically get to the story of a new virus immediately, thanks to metagenomics. Metagenomics is probably the only scientific technique that you can explain with a hyperbole and a half meaning. Metagenomics is sequencing all the things. And I guess you have to sequence all the things. Yeah. Kelly is doing metagenomics. She is sequencing all the things that come out of rats. So what you do with metagenomics, it's fairly straightforward. You take an environmental sample. It could be, a cup of water from the ocean. It could be rat feces that you've harvested from Kelly's dumpster. It could be the blood sample from, I'm sorry I referred to it as your dumpster. It's really the people's dumpster. And the people's rats. So you pick an environment, you break apart all the cells in that environment, you pull out the DNA from all of those cells, and you read what's in there. So if you were, harvesting the feces of one of Kaylee's rats, you would probably get some rat DNA, you would get all sorts of bacterial DNA from whatever's in the rat's colon, you might get some DNA from whatever foodstuffs the rat had been eating, like 7-Eleven hot dog DNA or something. And by comparing all of the sequences that you get against a database, you can identify this sample is 99% rat, there's 0.5% 7-Eleven hot dog, there's 0.2% E. coli. You get a list of what's in there. So when we're doing metagenomics to find a new virus, what we would do is take a sample from our patient. It might be blood, it might be cerebrospinal fluid. We break open all the cells, we sequence all the DNA, we throw out the human stuff because we know that's coming from our patient. We throw out the stuff from the bacteria and the viruses that we would expect to find there, your sort of regular flora, your microbiome, and we just look for what's left over. We look for what's interesting, what's a pathogen, what's not supposed to be there, what's something that we've never seen before and doesn't have a match to anything else in the database. And that's how we start to figure out what this new agent might be. A great example of this, a couple of years ago, it didn't pan out, unfortunately. The headlines had so much promise for the end of days. New virus in Africa, looks like rabies, acts like Ebola. if you had to pick the two scariest pathogens in the world, they'd probably be rabies #1 and Ebola #2. So imagine my excitement as a disease controller. Turn on the news and everybody's like, oh, rabies, Ebola. So you're like, oh great, this is my time to shine. And it turns out, when you're a really terrifying pathogen like rabies, Ebola, you can't actually spread very far before everything just kind of goes up in flames. And that's exactly what happened. 2009, there were a couple of very weird cases of what looked like Ebola but didn't test positive for Ebola in the DRC, the Democratic Republic of Congo. And so scientists that were interested in figuring out what is this some sort of new, interesting hemorrhagic fever, did this metagenomics approach. They took samples from the patients that had gotten sick, sequenced all of the DNA that was in there, threw out the human DNA, threw out the regular stuff that you'd expect to be there, and what they found was a virus that looked like rabies. Its closest relative in the database was rabies, but it caused a syndrome that looked like Ebola. So this sort of metagenomics technique, we've used this time and time again to discover novel pathogens. If there were a zombie outbreak, this is probably the first thing we would do. We would grab some sort of string of rotting flesh from a zombie that happened to be shuffling past. We'd wear gloves, of course. We're very safety conscious and safe. We'd grab a string of rotting flesh, pulverize it, sequence everything that we found in there, throw out the human DNA, and look for what was left over. And that would help us find out, what the fuck this thing actually is. Having answered that question, the next question is HTF. How the fuck is this thing spreading? And it's here that we go from the lab to the math domain, and we encounter what's probably one of the most fundamental concepts in epidemiology today. So fundamental, it actually made it into contagion too. This is something called R0, or the basic reproductive ratio. And R0's a very simple concept. It says for every one person who is sick, how many secondary infections will they cause? If you have a completely susceptible population, how many other people will get sick as a result of this one person's infection? There's a lot of math that goes into R0. I will just summarize it as this. I will summarize it with words instead of terrifying math shapes. Words are this. It's okay, I'll give you terrifying math shapes later. I'm just going to ease you in right now. You can get another drink before we get to the terrifying math shapes. R0 is simply a function of three things: the transmissibility of a pathogen, so how infectious is it? Do I have to cough a lot of it onto you? Can I just cough a little onto you to make you sick? Incidentally, if you come say hi after, I have a cold right now, so don't get too close. Stay in the zone of exclusion, and if I don't shake your hand, that's okay. I can CDC elbow bump, the properly endorsed way of greeting somebody when you're sick. So transmissibility, it's true. During the swine flu pandemic, you actually saw political leaders, including Obama, doing the elbow bump, which is really cool. Yay, public health. So transmissibility, how transmissible is the pathogen? How likely it is to make others sick? We have to also consider this in terms of the contact rate. A pathogen can be extremely transmissible, but if your population, if your people aren't coming into contact with each other, if they're not, sitting overstuffed into a crowded old porn theater, your pathogen isn't going to get anywhere. If you have a pathogen that's not very transmissible, but you have conditions like this, suddenly the opportunities for transmission increase somewhat. And you also have to consider duration of infection. How long is somebody sick for? The longer they are, the more contacts they'll make, the more chance they have to pass things on. So when we calculate R0, we get a number. We get a simple number, and if that number is greater than 1, the epidemic can sustain itself. The disease can keep transmitting in your population. If R0 is less than 1, it's just going to peter out at some point. And if you have a population that isn't entirely susceptible because they've been immunized, they've been vaccinated, it's easier to get your R0 below 1. We can also, with our R0 value, calculate another important parameter. if we do, this is probably as mathy as it's going to get. If we do 1 minus 1 over R naught, there's my air math for you, that tells us the proportion of the population that needs to be immune to something in order to affect herd immunity. This is something we hear a lot about these days, thanks to vaccination refusers. And depending on the R naught, you're going to get different values for 1 minus 1 over R naught. If you've got something like the flu, its R naught is typically kind of 1.2 to maybe at the most 1.5. So only about 2/3 of your population needs to be immune, either through natural exposure or through vaccination, in order to really keep flu from spreading through your population. If you have something like measles, which has the highest R naught on record, R naught estimates vary from outbreak to outbreak, but for measles, the highest that's being reported is 20. So if you do 1 minus 1 over 20, you get 0.95. 95% of the population needs to be immune against measles in order to affect herd immunity, which is why measles is coming back. So, the first thing that we would do in a zombie apocalypse, besides throw all the anti-vaxxers to the zombies first, would be to calculate R naught and figure out how much of a bad time you're actually in for. The third thing that we would want to answer, this is probably the most important thing, is what the fuck can we do about this? So there's a terrible rabies Ebola virus on the loose. Its R naught is, 10, and we're all going to die. What do we do? And to this, again, we turn to math. We turn to math modeling. I'm so sorry for this. I can't help but make horrible puns, and when I can do them visually, it's even worse, because you get that moment, it's almost like a paper cut, where, you cut yourself, and you're like, oh, that's really going to hurt in a second, and you put this slide up, and you're like, oh, that's going to be terrible in a second, and then people are like, that joke is awful. So thank you for not throwing anything. So math modeling. This actually, if you're curious, that is one of the equations that you use to figure out from parameters that you can collect really early in an outbreak, things like the number of cases, how long it's been. That's the math that you use to actually calculate R naught. This is probably the first time that type of math has ever appeared on stage at the Fox before. I don't remember that from Deep Throat. I don't think So, math modeling actually has an illustrious history. It goes much farther back than Deep Throat. It goes back to Bernoulli. Bernoulli, who of course gave rise to the Bernoulli principle, which is why you can all fly around in airplanes. Thank you, fluid dynamics. Bernoulli was the first person to do infectious disease math modeling. And back in the days when smallpox inoculation, as espoused by Edward Jenner, was sort of coming on the scene, Bernoulli calculated that the effect of smallpox inoculation on population life expectancy was to increase life expectancy from 26 to 29. So kind of rock star style, like I hope I die before I get old. That was just how things rolled back in the smallpox era. But Bernoulli was really the first to actually show that, yes, you can use math to make important health decisions and rationalize things. And so we use math to this day in making public health decisions. We use compartmental modeling. Compartmental modeling is actually pretty straightforward. Compartmental modeling is compartments. You're not supposed to put people in boxes, but in compartmental modeling, that's exactly what we do. We put people in boxes. In the easiest form of compartmental modeling in an epidemiological context, we do something called SIR modeling, susceptible, infected, recovered, and I put an asterisk by recovered. Asterisk is very hard to pronounce too, by the way. Recovered is sometimes termed removed, because you can be infected and you can recover, or you can be infected and you can be removed from the epidemic, which is a very polite way of saying you've died. Math is a very graceful terminology. I'm so sorry, they've been removed. We should use that more often. So, compartmental modeling, you've got your S box, you've got your I box, and you've got your R box. So for a given population, we might be modeling the entire population of Vancouver, all of BC, loads of heads off, whether they be a nuclear strike to wipe out a whole horde of zombies. That's what you're supposed to do. So if there were a zombie apocalypse, we would be at CDC sitting around a whiteboard doing math, because that's what you do at the end of the world, you do math, figuring out what the compartmental model looks like. We'd be coming up with ideas for different interventions and figuring out which of those interventions might actually work. So that is world's briefest introduction and, zombie apocalypse 101. If you remember anything from tonight, it should probably be that our address is, I promise you, 655 West 12. There's a back door in the alley. There's a keypad. I'm not going to give you the code because you need a swipe card to also get in. But talk to me later. We can arrange some sort of special knock signal or some sort of little bat thing. And if you're like, hey, I was at Nerd Night that one time, I will let you in. I will offer you CDC asylum. And yeah, we can drink whatever beers are left at the end of the world and talk about math modeling. So with that, thanks. I'm happy to take any questions about random cooties, potentially math, whatever you want to know. And thanks for coming out tonight. So
I usually like to banter about the substantive content of the talk. I can't get over the deep throat comment on the film, and I just love that it came to you so quickly and so naturally. And then I really wish that you talked second, because then we'd have Twitter questions where people could come up with something this themed for a porn film. So just do that on your own.
Debbie does derivatives.
What was the first part of that?
Debbie does derivatives.
Debbie does derivatives. Communication is amazing.
I feel like I should unclip this.
That is Debbie, and she just did a derivative. We're going to open the floor up for questions for Dr. Gardy. Do you have any questions? It feels wrong to call you doctor after, but maybe it feels better to call you doctor.
Even just call me cat lady.
Cat lady Gardy over here. Do we have any questions? We're going to start off back there. Yeah.
Sort of a weird question, but do you have any idea what the R0 was for the Ebola crisis that was in Africa?
Oh, that's a great question. I can't tell you off the top of my head, but I suspect it was around 2.5 to 3. There were figures bandied about, but I haven't looked at them in the last year, so it is small-ish. Ebola is interesting because we can cure it, well, not cure it, we can prevent it with soap. Ebola is fundamentally a failure of infection control, and it's something that is it's characteristic of under-resourced health systems, which is why you never saw any onward transmission in any of the countries that received Ebola patients except America. But that was Donald Trump's fault. Let's just blame it. He wasn't even running really then, but still, it was his fault. As long as you've got appropriate personal protective equipment, you can kill it with a dilute bleach solution too. So R0 would be highly dependent on where you were too. But I think it was around 2.5 to 3.
Does the CDC here have any statutory power to act? And if not, why not?
Excellent question. It was, does the CDC here have any statutory power to act? And if not, why not? I don't even have to answer the last part of the question because we do, and it's called the Public Health Act. Hooray! Yeah, it's called the Public Health Act. The Public Health Act is something that gives us power to do almost anything that we want, but we rarely have to actually enact it. The times that we do enact it, it's typically on kind of an individual patient basis, and it'll be a scenario. Most of the work that I do is on tuberculosis and understanding TB spread, and the downtown east side and other areas where you have kind of underhoused and vulnerable populations tend to be sort of hotbeds for TB transmission. And if you've got somebody that is extremely infectious with TB and they're not compliant with their treatment, through the Public Health Act, we can do things like, pick them up and bring them to the TB ward and hold them there. It's a nice hold. There's games and the internet and stuff. It's not prison or anything weird. But we can do these sorts of things to take individual people off the streets and keep them healthy.
To follow up, can you potentially breach charter rights?
Ooh, can we breach charter rights? Probably, but I don't know.
I'm just curious.
Yeah, no, I'm not sure. That's a question for my boss, the Deputy Provincial Health Officer, because she knows everything about HIPAA and FIPA and every acronym that we are supposed to be beholden to. Good question.
Maybe another question? Yeah.
Just to follow up with that, if you can, in order to be able to hold people, like on the TV ward, do they have to be confirmed cases or can they be suspected?
They can be suspect cases, yeah, because the thing with TB is it grows really slowly. And so our current approach for diagnosing and confirming TB can take from when a sample comes in, typically, if it's a really high bacillary load, if somebody's got a lot of TB in their sputum, it might be sort of 6 to 7 days before our machine dings positive and says, there's TB in here. If it's somebody that has less TB, but they're still coughing it out and it's still infectious, it might be a week and a half, it might be 2 weeks. So because those periods are sort of prolonged, if somebody has highly suspect TB, we're pretty sure it's TB, and that person is a risk for going out into the community and being non-compliant with the measures that we tell them to be compliant with, like wearing a mask. TB, you can stop it with a paper mask. It's pretty straightforward. But if we think that person isn't going to be compliant, we can have them on the ward until they're either confirmed and then put on treatment or confirmed as negative and sent out into the world. And one of the things that we do with our genomics work is saying, well, how can we make that faster? How can we take that, week period, that 2-week period, where we're trying to figure out, does this person have TB? And if so, what antibiotics is it sensitive to? What is it resistant to? What should we be treating them with? Can we accelerate that using DNA sequencing so we can get that time down to, a day or 2 days instead? So it's all about making things better for the patient.
We're going to take one more question. Well, we have so many. I'm going to put this up to you because I don't want to be the bad guy.
Oh my gosh. Okay, well, Jake, I know you, so you can ask me a question anytime. Let's go there. The gray shirt. Yeah, you right there that just look behind you.
In terms of the effectiveness of sequencing all the things, is it a function of how much you know about what's in your environment? So say if you went somewhere that was the tropical environment with a lot of different things you didn't know, would metagenomics be less effective?
That's an excellent question. When you sequence all the things, how much is it a function of what you already know? Because as I said, one of the steps, you sequence all of the things, and then you have to compare all the reads that you got, all that sequence information, against the database of everything we know in biology. And depending on how complete that database is, you might get the right answer, you might not get the right answer. So sometimes you'll identify something totally new, you've never seen it before, but it looks kind of like something you've seen before. So it turns out that there's sort of signatures that particular viruses or particular bacteria might have, just ways that their DNA are written, kind of an alphabet or a language that they prefer. Just like, you might pick up a novel and read just a paragraph and instantly know, like, oh, this is a Dickens because there's no punctuation in this entire paragraph. You can kind of do the same thing with DNA sequences. You can look at them and you're like, this kind of looks a lot like a rabies virus. So even if there's not an exact match, even if it's something totally novel, you can still kind of make inferences about what you're seeing that can be pretty helpful. Great question.
Great, so we're going to leave it there. I'm sure if you have additional questions, as long as you stay outside of Dr. Gardy's zone of exclusion, you can come and ask them to her. But another warm round of applause for